Well, let's continue. So we have seen for the current number 1, the error vanishes. We have seen it for the first leading terms, but it proves also to be true for the others. So for current number equal to 1, the right-hand side, so this stands for right-hand side, of the modified equation of the explicit upwind method, which was 24 that we just derived before the break, proves to be 0. And that means that the explicit upwind method exactly solves, or is exact for solving the linear Becksch equation. Why is that so? Well, when C is 1, current number 1, then the algorithm that we use to compute our unknown at the new time level yields ujn plus 1 is equal to, and then we had 1 minus cujn plus cujn minus 1. So we get uj minus 1 n. So that is what we get. We give this a number. 25. And it says the following. If we look now in the xt diagram, where we have our unknown, say here, xj, and we assume we have our unknown xuj minus 1, this grid point xj minus 1, we want to determine the solution at the new time level. So here we have the time level n plus 1, say delta t, and here we have n delta t, the old time level. So then we argued when we derived the stability condition that the characteristic must come from a point that is between these points. But what when we have this situation? That is allowed when we have this situation. In this situation, the distance traveled by our unknown in the time delta t is c delta t. So when we start here and we let it go for a time delta t, then the solution will be here. So that corresponds to saying that the slope of this characteristic, here we have delta t, that is 1. And we have here delta x. So in that case, c delta t, the time traveled, and the grid spacing are the same. And that is the same as to say that the current number is 1. So the current number is c delta t divided by delta x. If that is 1, then these two are equal. And then the characteristic to our unknown at the new time level, at the unknown location, at the unknown time, the new time is coming from where we have the solution. And that is the solution at the grid point j minus 1 at the old time level. So, and we know the solution is consonant characteristics. So when we have this solution and we have this special case, then the solution from here will be transported here. So then we have the exact solution. And we can also understand that by looking at the exact solution. So that is 25 is exact because we have u of xj tn plus 1. That is what we want to compute. Then we know from the exact solution, if we assume we go back to the time, to one time level, then we know that the exact solution will be then xj minus c delta t at the time level tn. We have seen that for the exact solution going back to the time 0, but we can just go back one time step delta t. So then, and that is what we argued already before when we derived the stability condition. On the characteristic, the solution is constant. The characteristic will come from the point xj minus c delta t. That is clear when we have the characteristic with the slope c. And in this particular case, when the current number is 1, this distance the solution has traveled in the time delta t is delta x. So that means this is delta x in this case for c equal 1. And then we have here that we have the solution at xj minus 1 t. And that is when we interpret that as look at the numerical solution then. This is the numerical solution ujn plus 1, to the one that on the right is this one. So then we do exactly the right thing. So this is 26 number. So then we can see that indeed in this particular case we get the exact solution. And you will look at that for the case when c is negative. Then you can do similar reasoning, but then your characteristic will not go this way, it will go that way. So then you can think how you should choose then your c to get the exact solution in that case. So that has given now us already some new insight into the explicit upwind method. But we are not yet finished. We can still go on and analyze more, and we do that. And that will be now by looking at the stability of the method. We have looked at the stability by consideration of this kind, from the characteristic coming down at the point of the origin of the characteristic being between these points, but that was a more, say, heuristic way and a more intuitive way. But we want now to do a more mathematical way, and that is the von Neumann stability analysis. So then we do the von Neumann stability analysis. Of the explicit upwind method. That is 17. So then we follow the recipe that we already did for the forward time-centered space scheme for discretized and linear direction equation, where we found out that that was unstable. We insert Fourier node for wave number k, uk hat n. That is the amplitude of the wave with the wave number k at the time level n times this trigonometric form, which we write as e to the I kxj, which we know is cosine kxj plus I sine kxj, which makes it easy to do the analysis. We insert this Fourier node for ujn into the equation, and it is better to use the form 18. Of course, then we have already written it as the algorithm unknown left and known right. So the form 18, just to remind you, that was ujn plus 1 is ujn minus c, is the current number, ujn minus uj minus 1. And we do this again for c greater than 0. So when we add that here, c is greater than 0. That is all when we do it in that way. And you'll do that for c smaller 0. So now we do that. We insert then Fourier node at the new time level, because it's n plus 1 on the left hand side, e to the I k x j. And that is then equal to, now it's the Fourier node for wave number k at the old time level, and this exponential minus the current number. Again, this expression, uk hat n, e to the I k x j, and then minus the Fourier node wave. The amplitude of the wave is again this uk hat n. Now it's e to the I k x j minus 1. So that is when we insert it in here. Now we divide by e to the I k x j. So we divide this one e to the I k x j. And we get u k at n plus 1 is equal to, and here we factorize the uk at n. So then we get a 1 from there. We get the current number. Here we get also a 1. We have divided by that. Here that is factorized. Here we divide by e to the I k x j, and we get e to the minus I k delta x, because this is xj minus delta x. Then we get it in this form. And that is then times the u hat k n. So then we see what the amplification factor is, that is what is in square brackets. So then, and then we use also the Euler's formula. Euler's formula for this term here. Give us the e exponential is the cosine of the argument, which is minus k delta x. Cosine does not distinguish plus or minus, but then we have minus the exponent, the imaginary unit I sine k delta x. So that will then be the result from the Euler's formula for this. So we'll use that to express now the amplification factor. Amplification factor of the explicit upwind method. This form is then 7 g of k delta x, and that we write, instead of we write beta, is 1 minus the current number, and then we have 1 minus, then we take a cosine, so we write beta for k delta x, and then we have here a minus from this, but in front we have also a minus. So then, let's see if we have still the minus. I think we have to we have the minus minus, so that's therefore plus, it's right. It's I sine of beta. And that is a bracket around this. And the beta is equal to k delta x. So this is the amplification of the explicit upwind method. And the stability condition is that this should be an absolute value smaller or equal than 1. Absolute value should be for all relevant beta, and that is the same as to say g of beta squared smaller or equal than 1. And it is for all beta, and the ones that are interesting are the ones smaller or equal to pi. So then we have to check that. And now we have actually here a complex amplification understood, as we had also already for the forward time-centered space. So then we use the same rule for taking the absolute value of a complex number. And that is, if we want to have that squared, we take the real part squared plus the imaginary part squared. Plus the imaginary part of g of beta squared. And then let us look what is the real part here. Well, I will need a little bit more space in here. So the absolute value of the amplification factor squared is equal to the real part. The real part is 1 minus c minus, that is 1 minus cosine. So that is the real part. Plus the imaginary part is then minus c sine squared. So then we have to do a little algebra here. So that gives 1 minus. So we take binomial formula here 2 times 1 minus cosine beta plus this squared, c squared. We take immediately this squared. It's 1 minus 2 cosine beta plus cosine beta squared. And from the imaginary part, we get a c squared sine squared of beta. So now we can observe something nice. This term here and this term times this term, they add together to c squared, because sine squared plus cosine squared is 1. So this gives us addition 1. So we get here the 2 times minus 2 cosine beta. And we see we have the same thing here. We have already here the 2, we have this, and we have a c here. So we can factorize actually this here. So we get then that this is equal to 1 minus 2c 1 minus cosine beta. And now we have factorized. This is 1. And from here, we have here the 2 from this. So we get the 2 outside. We have a 1 minus cosine c squared. and we have here a minus, so we get here a minus C. So that is what we get here. And this is now our amplification factor squared. So that means we have to require that this is smaller or equal than 1 for stability. Now we see the 1 nicely goes away. So the stability condition, amplification factor squared in absolute value, smaller or equal than 1. That is then equivalent for saying minus 2c, now we write the 1 minus c directly behind, times the 1 minus cosine of beta is smaller or equal than 0 if we subtract 1 on both sides of this inequality. And then we remember that c is the current number, is the advection velocity, delta t divided by delta x squared. So, and we had done that for c greater than 0. So that means we are talking here about positive c. But that is just for an experiment. Think of what would be if c were negative. If it were not positive, it were negative. If c were negative, then we have a positive time step, otherwise that would make sense, delta x not 0, so that is positive delta x squared. So then the c will be negative. If c is negative, then we get here minus something negative, we get here something positive. That is then definitely greater than 1. This is greater equal than 0, and minus c will also be positive. So we will get definitely for beta not equal 0, we'll get on the left-hand side something that is positive. We can never get that true. So that means if we would apply the upwind method for c greater 0, for a situation where c is negative, the method would be unstable. That is what we can see here. So therefore we should use the method that we saw in the beginning for c negative, where we take the value from where flow is coming, that is then to the right, not this one. But here we are talking about c positive, so we have the case that c should be greater than 0. If c is greater than 0, that is okay. 1 minus cosine beta is greater equal 0, so that is okay. But this guy here has to be greater equal 0, because we want to keep this minus sign. So if all the rest is positive, then this will give us something negative, and such that this inequality is true. So what we can see is that this, or both inequalities, or this inequality is satisfied if c is greater than 0, because the opposite we just discussed, that will not lead to anything useful. And we will also need what we just argued, that 1 minus c, that has also to be greater than 0. So that means the condition that we get from here is that this inequality is satisfied if c is between 0 and 1. That is exactly what we had derived by this heuristic arguments for the characteristics earlier. And that is then the CFL condition. So the conclusion is that the explicit upwind method is stable for what we call the CFL condition. That we write it again, 28, it's the same as we have here, when the current number is between 0 and 1. So where C is C delta t divided by delta x, this is the current number. And that is again now we have derived it really with this tool. That is the CFL condition. So that means if the CFL condition is satisfied, then the explicit upwind method is stable. Now we can say even more, because we know about Lex equivalence theorem. And that says if we have a consistent finite difference method, then stability and convergence is equivalent. We know explicit upwind method is consistent, it's first order in time and space. And then if this condition is satisfied, the CFL condition, then it is stable. So that means if the CFL condition is satisfied, then by Lex equivalence theorem, the method is convergent. Just state that by Lex equivalence theorem, the explicit upwind method is convergent if CFL condition is 28 is satisfied. So that means that the numerical solution that we get with the explicit upwind method will converge to the exact solution of the linear advection equation as we refine delta x and delta t. Okay, so that is useful that we know that we are really getting close to the exact solution when we use this. I've also seen that the choice C equal 1 is a particular good one, because then the method is actually exact if C is positive. You will find out how to choose it, to choose the current number when C is negative, to get the exact solution. Now we want to look at the situation for what would we get for the amplification factor for the exact solution of the linear advection equation. Then we can compare the amplification factor for the numerical method and for the exact solution, and can draw conclusions from that. So that is then the exact amplification factor that we want to look at now. And that is obtained, that is the exact, that is obtained by inserting the Fourier node, and that is the following, 29. Now we leave that continuous in time, that is the trick here, and we make the assumption that we have some trigonometric expression in space. We call it the harmonic mode in that case. So, as before, as what we also used for the von Neumann analysis, that we assumed a form of the solution with trigonometric expressions. This is cosine plus I sine. X. We insert that into the equation that we want to solve. That is the 1D linear advection equation. That is equation 1. So if we do that, we get the time derivative of this Fourier transform, the amplitude of the for wave number k, e to the I kx. So that is the time derivative of du dt. So we say u is like that. Then we get this. From the time derivative. From the space derivative, we get the first derivative with respect to x. So we get an ik in front. And we have also the c. So we get c times ik, that is coming from the first derivative. Then we have here the uk hat of t, e to the ikx. That is equal to 0. So we can divide by e to the ikx, and then we get that the time derivative of our Fourier transform u hat for wave number k is equal to, and now we put that on the right hand side. We get minus c I k u hat k. And this is a simple linear ODE of which we know the solution. So the solution of that is that this amplitude of this Fourier transform is equal to the value that we have for time equals 0 times e to the exponential, e to, now we write the I in front, I c k t. This here comes, gets the exponent. If we do the check, we'll find out that will satisfy this linear PDE. Now we can also express this by getting in the delta x. And let's see, yeah, we can do that when we, so that we have the exact solution. And we want now to know the solution for, say, a time step after time step delta t. So then that is equal to the u hat k of 0, e to the minus ic wave number delta. And here we can get in now our delta x to get it then linked to what we had before. And that is then, let's see, that is then equal to u hat k 0, e to the minus I, and then we can get in here the c delta t, to summarize that, and we get here that we divide by delta x, and then we have also to multiply by delta x. Why do we do that? Because we want to get in here our Courant number. So that is the capital C that we get in here. And then we see from that, so this is from getting from time 0 to time delta t, but it would be the same thing. We would get the same factor getting from time level n to time n plus 1. So from that, we can then see that the exact amplification factor, if we express that as a function of k delta x, that is what we want, then we get it in this form. Then it will be e to the minus I Courant number k k delta x. So this is a number 13. So this will be then the exact amplification factor. And the c, I remind it again, is the current number. C delta t divided by delta x is the current number. So, and now we can compare this exact amplification factor with the numerical one that we have for the explicit upwind method. One thing that is quite obvious is, if you think of the Euler's formula, this is a cosine of this plus I sine. If we take the absolute value, it will be 1. So that means the exact amplification factor does not change the modulus. The absolute value stays the same. But what we observed in the numerical experiments and what we also saw, that is not the case for the numerical one. The numerical one is actually decreasing. So we get a damping of the waves. And this is wrong. You see here, the amplification factor should stay unchanged. And the size should not change. So that is one thing. And the other thing is that from this here we can see also how the propagation should be. You can see the propagation in this form here. When we have it in this form, the amplification, this is the advection velocity that is coming in here. And that is then telling us about the propagation of the solution with the advection velocity c. If we have a numerical method, this will be changed. We will get an error here, and that will mean that we will get this expression here that we have here, that will be wrong. So we can either attribute it that we say we have a wrong advection velocity c, or that we have simply a wrong wave number in that case, when we do it numerically. But this term here, that is then called, that is deciding then on the propagation, that is called the phase angle. And you see why it is the angle, it is cosine an angle plus I sine angle, that is there. So the angle that is coming in here, that is 31, phi e it is called for exact, that is minus c k delta x, which is in our c times beta when we use this abbreviation for beta. That is called the exact phase angle. Now we can also then compare the phase angles that we get for our numerical method with the exact one. So let's see. Now we use a representation that we can have for any complex number. The amplification factor now we look at the explicit upwind method, that is we derive, that is 27. Our G of beta and so on can be written as 2 G of beta is equal to the absolute value. It tells us then something about the modulus, whether according to the exact solution should be stay 1, but in our case it will be smaller than 1. We will have damping e to the I phi. We can express that. And in here, the phi is then the arctangent of the imaginary part of g of beta divided by the real part of g of beta. That is the idea is coming from the real part of, say, a complex number z and the imaginary part of the complex number z. We have x here and we have y here. You can imagine that is our complex number z. Then we will have this angle here, that is the angle phi. So the x is then the real part of, in our case, the amplification factor, and the y is the imaginary part of z. And we can get that angle by taking the imaginary divided by the real part, then we get a tangent. This is then the tangent. From that we get this angle then that we can, that is then the phase angle. That is called the phase angle. This angle that we get from here is the phase angle. So this phi that we have here is called, so the phi is called phase angle of the explicit upwind in that case. So then we can compare that with the exact phase angle. That will tell us something about the dispersion error. The modulus tells us something about the dissipation error, that the amplitude get damped, which should not get. And the phase angle then tells us something about the error in the propagation speed, the dispersion error. So that is something that we shall look up at next week, and then we shall look also at other numerical methods. We have now concentrated very much on this explicit upwind method because that is really very important, and from this we can get even more insight. But you will get more insight by doing exercise 6, and then see what happens when we have a propagation from left to right. Okay, I will stop here.